Hey guys, we are back looking at this spring and box situation, only it's in the horizontal. And we've seen horizontal and we've seen vertical. And now I want to combine something that we were just in, energy transfer, with what's happening here. Let me show you guys something that you guys are probably familiar with if you did this. At home, you could stretch this out and you let it play, and it eventually comes to rest as friction slows this thing down. Now in this sweet program AlgoDo, I can take my wooden box and say, well, let's take this friction down to 0. Let's see what happens now. So now I'm going to drag my box back and let it go. So it's oscillating back and forth, and there's no friction wearing it down, so this will continue moving back and forth unimpeded in simple harmonic motion. Now, what I want you guys to think about is the energy transfer as time goes on and as this thing moves from one position to the next. Let's start by looking at the potential. So here's my potential in the spring, and it's oscillating in such a way where we would expect some curvature in our graph because the equation for the spring energy is 1/2 kx squared. So let's pause this at a couple points and try and make sense of it. If I pause it about where it's in equilibrium, now we're over here, and there's 0 potential energy. So up here is a maximum, here is 0, and that makes sense. We're at equilibrium, there's 0 potential energy in the spring, and when this thing moves forward, it's really compressed, and now it's moving up to a maximum. If I continue it forward, it goes out to where it's super stretched, and it's climbing to another maximum in potential energy. Cool. Well, let's explore what is happening to the kinetic energy. Let's erase this for a second, and then we'll play it. Well, it also is changing with time and position. When this thing is, let's say, at its most stretched point, we have 0 kinetic energy, and up here we have a little over 20 joules of kinetic energy, but here when it's far stretched out, we know its velocity is 0, so we would expect to see 0 joules of energy. And then it hits its equilibrium point, and that's where the energy of kinetic energy is maximum here. It's moving fastest, and then it gets compressed, and we have 0 kinetic energy. Now what would be interesting is to see the overlap here, and I think I can do it, but I don't think you guys can see how this thing is overlapped. So I had to do this on the board in order for you guys to be able to see what's going on. Hopefully you guys can see that. I'm going to just do a double take and also probably turn off my projector in order for you to see my board. I don't want there to be any glare. That's my chest that you're getting a view of. Okay. So simple harmonic energy transfer. I'm just drawing a wall diagram from when this thing is really compressed and it's all in spring energy, and then it goes to what I'll call the second snapshot as my equilibrium point. So the energy is transferring from spring into kinetic energy. And if there's no friction, there's no energy loss, so the initial energy will equal the final energy. So the total energy in the system is constant, right? There's 4 blocks here, there's 4 blocks here. At any point that I look at this system, there will be 4 blocks of energy. So I could find that energy total by adding up the kinetic energy and the spring energy at any given point along the system. Now, if I wanted to find the total energy, it's easiest to do this at an equilibrium point or at the amplitude point. So when x is equal to a, meaning that block was really stretched out or it was compressed, all of the energy is in the spring energy, and I could find the total energy in the system by doing 1/2 kx squared. Let me just adjust this for a second. Good. I could also find the energy of the system, the total energy, if I knew the velocity, say at the equilibrium point. I could say, well, all of my energy is in kinetic energy because there's no spring energy at equilibrium point. And I could write that expression. Remember, the total energy in the system is the same at any point. This could be represented with a graph like this. On my y-axis, I've got energy. On my x-axis, I've got displacement. Over here is negative A. So this would be when the block is compressed, all of the energy is in spring energy, and then it's released, and the spring energy dwindles down to 0. Meanwhile, the kinetic energy is increasing. So if I look at this position here, all energy is in spring, no energy in kinetic. I have this amount of total energy here. Now at x equals 0, it's just the opposite. There's no spring energy, all of it's in kinetic, but notice I still have the same amount of total energy. And then finally over here, once again the spring energy is a maximum, kinetic energy is 0, and I have the same amount of total energy. At any given point, the total energy is the same. What do you know about that? So long for now. See you next time.